So what have we got here? Chromium, nice. Atomic number 24. 6 D block. Transition metal. Not chromium the browser. Chromium the metal. Oxidation states. Body-centered cubic, just like vanadium. From the Greek word for color, chrome. Some very colorful
Chromium.
Stainless steel, an iron-based metal that is, by definition, at least 10.5% chromium. There are these subgroups. 410 and 420 are martensitic and can be hardened. For instance, the blade of a chef's knife.
Yeah!
Or the tradesman's tool. These are fairly low in chromium. They trade off their corrosion resistance for the ability to harden. Then you have the austenitic class, your 304 and your 316. These excel at being non-corrosive and non-magnetic. The reason they are said to be stainless or non-corrosive is down to the behavior of chromium. The surface does in fact oxidize, but in a non-destructive way. The surface chromium oxidizes, producing a green but invisibly thin film of chromium-3 oxide. This allows you to still see the shiny mirror finish, whilst protecting the metal underneath from reacting with more atmospheric oxygen.
Homer, did you polish your head in a shino bolo?
For this reason, it is used, 316 especially, in hospitals and places of food preparation. Passivation layer allows it to be kept clean and sterile. Trivalent chromium is biologically useful, but hexavalent chromium is extremely toxic. So, let me explain the chemistry of hexavalent chromium, starting with the chromate-dichromate equilibrium. First, we have our bright yellow alkali chromate. This can be sodium chromate or potassium chromate. Which one is irrelevant to this discussion. If you want to know the difference between the counter ions, the potassium salt is favored for lab scale use. It's more stable, it's more expensive, it's less hygroscopic, and less soluble than its sodium counterpart, making it useful when growing crystals or doing titrations, etc. The real differences are with the dichromates. When potassium chromate dissolves into water, we get chromate ions. The solution, just like the solid, is a bright yellow. We have little tetrahedral molecules with a chromium atom in the middle and 4 oxygens. When dissolved into freshly distilled water, this is usually around pH 9. This is a deprotonated alkaline solution. I suppose we can draw this flat like a cross. It is said to have 2 double bonds, 2 single bonds, and a net charge of -2. So you might ask, are these double bonds alternating, or do we have double bonds one side and single bonds on the other? No. A single bond to an oxygen gives us a negatively charged oxygen, and the double bond gives us a neutral oxygen, and this is how chromate is often drawn. However, the true structure is more interesting. It's called a resonant hybrid. The two charges are averaged over all four oxygens. We call this delocalized pi bonding. This can be confirmed by looking at the bond lengths. Ordinarily, chromium to oxygen single bond is 1.79 angstrom, and the chromium to oxygen double bond is 1.60 angstrom. The chromium to oxygen bond lengths in chromate are in between those. They are all 1.65 angstrom. If we were to introduce a torrent of protons to our toxic luminous yellow bath of cancer coil, an oil of vitriol with H+ ions up the wazoo and dripping with acidity, our chromate won't be able to resist. What happens is, these oxygens, they become protonated one by one. Our solution is falling into an equilibrium of chromate and hydrogen chromate, and the bright yellow will lessen in intensity the more protons are transferred. Once our chromate has two of its oxygens protonated, it will find another in the same predicament and link up as one dichromate ion. Our suspicious 7-Up is looking more like a forbidden Fanta. As we keep adding more concentrated sulfuric acid, protonating, condensing, a fully protonated species referred to as chromic acid, H2CrO4. The solution transitions from orange to a very deep red. You could imagine adding more protons to create H3CrO4+, but sadly, this is too unstable to exist under normal conditions. All we can hope to do is dehydrate this with more acid, eventually giving us its anhydride, chromium trioxide, which is a red solid. Chromic acid is a very powerful oxidizer, and it is great for cleaning glassware. I've known it to set fire to organic residue. Whenever working with hexavalent chromium, you need to have a plan for how you're going to dispose of the toxic chemical. One method I find good is to reduce the hexavalent chromium to chromium 3+ using hydrogen peroxide. You get an intermediate, beautiful blue color, and that is unstable chromium 5+. What you get is something called chromium oxide peroxide. It is difficult to isolate as a solid, but it is possible within a matrix or within an ether solution. I think ether can stabilize it. On a pH acidity dehydration continuum, we might expect to see chromium hydride. So I'll mention it. Chromium hydride. Mil. stir our and stirring on. Turn the heating on as well. Move the heating probe. Thought this was better. Acetic acid is not strong enough to attack the stainless steel of the temperature probe. As this warms, it should dissolve. In the meantime, we will prepare our oxidizing agent, which will be 10 grams of chromium trioxide. There we go. 10 grams. This will be dissolved in water to make chromic acid. See, it is slowly going into solution. Tree fell in there. This is not good. Added a better condenser, and I'm going to heat this to 110 degrees, where the acetic acids start refluxing. I do like this condenser. Highly efficient, fluid condenser. I did some joinery. It looks like it's about to start raining. You can see just starting to boil. 107. To the chromium trioxide, I add 10 milliliters of distilled water. This forms a chromic acid solution. Chromic acid is highly corrosive. To this we add 25 milliliters of glacial acetic acid, 10 at a time. We will charge this addition funnel. And since this anthracene doesn't want to dissolve, I'm going to proceed with the next step. I will begin adding the chromic acid in acetic acid to the anthracene in acetic acid. Heating is not required as the reaction will proceed with a reflux because it's exothermic. Already see some chromic acid got in there and it's oxidizing the anthracene. I haven't even turned the stopcock yet, but there was some. Look at that blue color. I was expecting green. It is a bit green. Yes, it's green now. There's this. It's added dropwise. The chromic acid is added too fast. A vigorous reaction happens, which I will demonstrate. This is not ideal, so slow addition is better. This can be left to cool down. Okay, I will let this cool. Cooling water. going to use to water my plants. Once this cools down, I'm going to pour it into some ice water. Here goes some ice. Now, that's the Chromium should be in there. You can see the particulate matter in there. This is kind of like not very frozen ice cubes, but it's going to be cold. So if I can get that into here, plus the ice. Giving this a water washing. Taking a long time to dissolve, and a lot of acetic acid. It has all dissolved, so all we need to do is let this cool slowly. Crystals already.